next problem, where we will use the algorithm of checking if two segments intersect, is given two convex polygons, check whether they intersect with each other. So it's possible that they will intersect from the outside only. It's possible that they will intersect like that. It's possible that they won't intersect because one will be inside the other. And it's also possible that they will intersect many, many times. An easy example is, for example, square and the second square that is rotated by 45 degrees. And it shows that also for some bigger polygons, say, I don't know, I don't remember name for that, but the same example shows that there can be many intersections. We don't care about that right now. I'm just showing you that in case you ever think that there will be at most two intersections, it isn't correct. And how do we check for two convex polygons whether they intersect? Each polygon consists of two parts. The upper part, possibly it's called upper envelope, the upper part and the lower one. And what is true for both of them is that x coordinates increase from left to right, okay, in the order of vertices in the polygon. So we have this part in this order, this part in this order. And it turns out to be quite easy. For one part, check whether it has some intersection with some other sequence of segments. So this is a sequence of segments. And for some other sequence of segments, we check whether they intersect. Because we also divided the second polygon into two parts. And now we just have four parts, two here and two there. And we should check each pair from different polygons whether they have some common point. And while the naive solution, the brute force, would be n times m, and m are sizes of polygons, just for each pair of segments check whether they intersect. We already know how to check it for two segments. Here we can do it better with some sweep line, what you should already know, like how to use that, because there was Hassan's lecture about that. We should sort points from the left, and you don't even have to think about sweep line. You just can assume that segments are sorted from left to right in both sequences of segments, and you use two pointers in those lists. Okay? We have, let's say, segments A, B, C, D, E, and segments X, Y, Z, W here. And it isn't necessary to check whether X and E intersect. What we should do instead is for two lists of segments, A, B, C, D, E, X, Y, Z, E, check whether A and X intersect, and check which one ends further to the right. Let's say that X ends further to the right than A. So now we don't have to check A with some segments on the right. Instead, we change pointer from A to B. And we check whether B and X intersect. So then we check X and B. Then I guess we check B and Y. So we can call that two pointers, or we can say that we moved with sweep line, because it's the same in this case. Anyway, the complexity will be just O of n plus m, because we don't even have to sort anything. The convex polygon already has his segments sorted. They go first to the right and then to the left, as we talked at the beginning of this lecture in the puzzle problem. So it isn't that hard. It isn't even hard to implement. The hard algorithm would be to check whether there is an intersection in some given set of segments. We are given some segments and we want to check that. So we won't talk exactly about that algorithm. So one quick question, whether Hassan talked something about this algorithm? Okay. So the quick explanation for this one, and it's solvable in n log n to check whether there is an intersection, and to find the number of intersection. If I'm not mistaken, it works in O of n log n plus the answer. If we are guaranteed that there will be only a few intersections, it will work fast. If there can be n square intersection, then don't bother with that algorithm and just implement the brute force that checks each pair. And in short, we use the sweep line, and when we encounter some new segment, we add it to the set of segments, current set of segments, intersecting with the sweep line. For example, if sweep line is here, and there are three segments x, y, z intersecting with sweep line in some set or some tree, we should store them in the order x, y, z. If there is, if in a moment we will add a new segment here, some points a, b, not a line, array, and there is some point below that. So let's say point with coordinates 5 minus 10 power 9. So far we checked whether A is on the left, B is on the right, and we would have to think what happens when one of them is exactly here. It isn't true. And the hack for that is to think that the let's say we have x equal to 5 here. The hack is now to think that the vertical direction is slightly rotated. And now if we check whether some point, previously we checked whether some point B was on the right or on the left from Ray. It was hard for points on the line. And now we remember, okay, I rotated vertical direction slightly to the right. It's now like that. So point B, if its x coordinate is 5 and it's above the point, some point S, the one from which we started the ray. If its x coordinate is equal to 5, we say it's on the right from the ray, because we imagined rotating rays a bit to the left. But we only imagined that. In our code, it means that checking whether point is on the right is for that we use the following code. X greater than 5 or x equal to 5 and y greater than y0 value. It turns out to be very similar to how we divided the plane into two half planes when we sorted points. Because all those ideas, hacks are quite similar, and they, you likely want to invent something smarter. Right now I just gave you some intuition how to invent that approach, upper envelope in one list. Of course it's sorted, the same for lower one. And for each point, binary search the segment that is exactly above P to check or below. And this allows us to count the number of times X-ray like that will intersect the polygon. Of course, in this drawing we see that the answer is 1. But the thing is that we don't know whether P is below or above the polygon. So we just have some P. It has coordinate X equal to some 5. What we do is we find with each segments. Usually there are two such segments. With what segments line X equal to 5 intersects. And then we also check point P had some Y coordinate. And we use that so one way is to find the exact intersection points and compare them with Y equal to something. But of course, it's harder way because we must find intersection points. The easier way is that we should just check whether for this segment point P is below that, and we know that it's on this line, so we just have to check whether it's on the left or on the right. So if this is AB, P is above the segment, if and only if cross product from A says that P is smaller than B, that is more on the left. And for so the binary search works for convex polygons. Also, it's possible to solve that in the same complexity. So something like Q plus N times log of something by using the sweep line and first adding all the segments and points, sorting them by X using the sweep line, and then in each moment of time for each sweep line we know what segments we have right now below and above, and for each new point P we just compare them with those two. And if polygon is concave, then there is no such easy way. We can also use the sweep line, but we can also use the sweep line, it's just that the binary search thing doesn't work. Now what we want to do is we want to check whether circle and polygon have intersection. And we can do that in O of n complexity. N is the size of the polygon.